Thanks very much. Yes, it was initially how to perform nuisance regression, and I realized I'm mostly talking about what you might not want to do. But the premise of nuisance regression is that we know something about the noise. We're not completely ignorant about the noise, and we can model a variety of noise confounds, and we can regress out any data variance that we have that looks like these confounds, remove that data variance, and what we're left with is a better ability to identify and accurately quantify the neuronal activity we're going to be interested in. So the majority of nuisance regression takes place in the context of the general linear model, so I'll introduce that. I'll give you sort of my take on what the current state of this field is, and then go into how do we make sure that we're using the general linear model in a statistically valid way. And then perhaps most importantly, some of the pitfalls that you might encounter as you're making a nuisance regressor or building and optimizing your noise model. These are automatically going ahead. Okay, just try this. All right, so first the general linear model. It's typically shown in this framework where y is going to be the weighted sum of the components in x with some residuals to that fit. So in this scenario, y is going to be your fMRI time series. It's typically been slightly pre-processed already. You've done something like volume realignment. And then your explanatory variables are going to be where you model your signal. And this is going to have your stimulus model. So if you gave a stimulus in a block design, that's where this regressor would go, but also all of these nuisance regressors that we're trying to build in. And then in the GLM fit, you're going to estimate these beta weightings. And the general linear model is really the workhorse of fMRI software packages. If you've done fMRI analysis, bog standard activation stuff, you've probably encountered it. So these are just some examples. FSL, it looks like this. In AFNI, you might use 3D deconvolve or 3D T-fitter, et cetera. And they already have many options to include nuisance regressors. So you see on the left, you can either choose not to add motion parameters, or you can add motion parameters very easily with the click of a button, or insert some more bespoke confound nuisance regressors. So how are we modeling the fMRI time series with a GLM? There's sort of three approaches. You might have task-based fMRI data that's done in a naive way where we're not considering noise confounds. We might then look at the same data with nuisance regression. Or we have resting state fMRI data with nuisance regression, and this is where I'm going to focus most of my efforts in this talk. So very conceptually, in task-based fMRI data, in a naive way without nuisance regression, you're saying the data is going to be some sum of activation that you've caused and these error terms. It's automatically going forward. I don't know if timings have been set. This will be exciting if it keeps doing this. So you can think about your total signal variance has to be apportioned into these two categories, your activation or the residuals. And what this means is you have a very huge pool of residuals in your model fit. And as I'll talk about later, that actually hinders the validity of the GLM when you have a giant amount of data variance being just categorized as unknown residuals to your fit. So we can do better than that. We can say, okay, we know something about our noise, and we can build that into our signal model. So we develop our nuisance regressors, and now our model is going to be the noise and the activation, and the error terms are then hopefully much reduced. So again, just with the same conceptual framework, you see the total signal variance is going to be divvied up in multiple categories now. So these are some example nuisance regressors you might have: motion, carbon dioxide, cardiac and respiratory information, signal drift. And now the variance is going to be distributed up like this, and your residuals are much smaller. And so we're appropriately identifying the sources of variance in our data. What happens with resting state fMRI? Well, here we don't have a signal model. All we have is our noise model. And so what that means is that the residuals to the fit include our signal of interest. So again, looking in this way, your total signal variance will be divvied up. We do not have a model of activation. So now we see the following, where our residuals are again very, very large and including our signal of interest. So what we see quite clearly is that, particularly in resting state fMRI, to have confidence in our signal measurements, to understand resting state fluctuations that are so interesting to us, this is entirely dependent on having confidence in this noise removal. Anything that we cannot identify as coming from noise becomes our de facto signal of interest. So nuisance regression becomes absolutely essential. So where are we at now? The current state of the field. Nuisance regression is really becoming routine practice. We've seen in the previous talks in this session things like retro I-core, motion parameters, RVT. A lot of these things are built into software packages and very straightforward to implement. So we are, as a field, having some consensus that these things are worth measuring and worth including, and we have systems to do it. But we do see that typical nuisance regression may not actually be sufficient. And this is my favorite quote. It came from an article, an interview that's cited there. It really, really, really sucks. My favorite result of the last 5 years is an artifact. Basically, there was a paper looking at functional connectivity networks, showing a difference between cohorts and development, and there was a beautiful hypothesis that could explain these results. And then the previous speaker has looked at some of these data sets and shown that there are systematic biases in head motion between these cohorts that can explain a lot of these findings. And so as a field, we're very concerned about the idea that we're not actually removing enough noise from our data, that the nuisance regression is not sufficient. So we see that our noise models have been expanding to avoid this issue. So head motion is a common one. We start off with 6 head motion regressors, our pitch, roll, and yaw translations, and our rotations and translations. We say that's not sufficient, we add the first derivatives. Maybe that's not sufficient, and we start adding these quadratic terms to look at nonlinear effects. So our models are just increasing and increasing to try to avoid the situation where there's noise left over in the data causing us to think there's some true neuronal difference in our cohorts. So we need to be careful about this expanding noise issue. So this is how I've approached it. So you model the data as some of your regressors, and in resting state, as I said, the residuals are your signal of interest. Now, typically, we look using ICA at these residuals. That's our clean data, and that gives us our signal networks that we would typically go on to discuss. But what about this variance that we normally throw away? What's in this that we're throwing in the bin during nuisance regression? And you can run ICA on that and look for structures in these noise networks. So when we do that, we see the following. We see these signal networks, it's typical things like visual network, sensory motor, default mode, everything that's very robustly identifiable. But what do we see in the noise? Even when we're just looking at the variance taken out by, say, 24 head motion regressors, we can see all of these network structures present in the variance that we are throwing in the bin. And even when we go down to just 3 head motion regressors, we see these same patterns. And this means that simply by chance, anytime you are removing variance that you think is noise, you might also be removing a bit of signal. So this leads us with this new position of a bit of conflict. We know that noise confounds are still a problem, but we can't just increase our models blindly because we eventually run the risk of throwing the baby out with the bathwater. We don't want to remove the signal along with the noise in this process. So what can we do? Moving forward, just before I get into this, some caveats. I am not a statistician. I share an office with one, and we have lovely chats. And I recommend you find a friendly local statistician and talk to them early and often. However, they, as was said in by previous speakers, they don't really agree with how we use the term noise. So get your terminology straight when you're talking with a statistician. I'm going to focus on resting state because it's trickier. Denoising and nuisance regression is the critical thing in defining what signal. A lot of what I'm saying will hold for task-based. But this is a very active area of research. Things are changing. When you're setting up denoising and picking nuisance regressors for your study, look at the latest and greatest literature because this is an active field. It's nearly impossible to know when we've sort of done just the right amount of denoising, this Goldilocks denoising, not too much, not too little, just right. And I'm not going to be able to tell you at all how you know that you're in this situation. It's a spectrum. So all we can really do is build confidence that at least we're doing the denoising approach in a really statistically valid way. So how do we make the general linear model valid? Well, it has statistical assumptions. We know that the system must be linear. Explanatory variables in X are independent, so nuisance regressors are orthogonal. We assume that the model is complete. You know everything that is happening in your data. We assume the errors are independent and identically distributed, heteroscedastic, so constant variance, and normally distributed if you want to make inference on the model fits. So are these assumptions met? I'll give you a hint, no. So here's an example. This is a CO2 trace and a heart rate trace. These are example nuisance regressors from one participant in one of my own data sets. And you can see, just by eye, they are strongly anti-correlated with each other. As you slow your breathing, your CO2 goes up, but your heart rate goes down. So we know that physiology in a given person will all be related to each other. And if you have more than one physiological regressor, these things are going to be linked. Head motion, if you move in one plane, you're likely moving in another. So they're not independent. And what this means is that we can't really differentiate between these two situations, where we've allocated the variance in our data to CO2 or to heart rate. We can't differentiate these two scenarios. Does it affect you? In resting state fMRI, nuisance regression, not too much, because in either situation, you're removing that variance and you're interested in the residuals. You're not interested in whether or not it was heart rate or CO2 that was explaining that. However, if you can't interpret the beta weights from the fit of your GLM, you can't optimize your model. So you're not going to be able to say, my model, I should be using these regressors or not others, or this is an optimal nuisance regressor for use in this cohort. In task-based fMRI, just as an aside, this is extra big of a problem. It's come up in the questions here. If you have task-correlated noise, so head motion when you press a button, or you hold your breath when you do a visual task, if you can't discriminate between these two scenarios, if you can't interpret the beta weightings, you can't then quantify your activation. So that's like a whole separate talk could be done on task-correlated noise, but I won't get into it here, but it is a challenge. So back with the resting state view, we were saying that the residuals to the fit, that's actually containing our clean data. That's our signal of interest. But that means the residuals are highly structured. And we also know we don't have a model of these intrinsic brain fluctuations before we begin. So this means the model is not complete. The errors are not IID, heteroscedastic, or normally distributed. So we're really not fitting the bill for GLM assumptions. So what can you do about it? Fortunately, there are tools available in standard packages, and the task fMRI world has really developed these thoroughly. And the one I'll talk about is pre-whitening. So the existing pre-whitening tools, I won't go into detail, but it's things like an autoregressive model or ARMA and ARIMA models. And the idea is that you can say, there's some structure in my residuals. I don't know what it is a priori, or I would have put it in my noise model. But what I can do is I can estimate the parameters to something like an autoregressive model. So I can sort of empirically decide what these fluctuations are, then go back and put that in my signal model. Now my model is more complete. My residuals are more white. That's pre-whitening. And so the question is, do these existing pre-whitening tools that we can easily just tick a box in something like FSL or AFNI, do they sufficiently model our resting state signal fluctuations so we could put them in during nuisance regression and make our GLM more valid? So I looked at that here. What you see is I'm plotting the total model R squared for a model of nuisance regressors. And the total model R squared is roughly proportional to the amount of variance you're explaining. And because it's nuisance regression, it's the amount of variance you're then throwing away. So on the left, you see the fit of true nuisance regressors. So that's a true noise model. I'm taking the real, this is frustrating. I'm taking the real regressors from that scan. Whereas over here, I have my null hypothesis scenarios, where I've simulated regressors that have nothing to do with the data. I've phase randomized the real ones, so now they have similar frequency content, but nothing to do with my data set. And on the final right column, what I've done is I've taken regressors from a different subject in a different scan. So yeah, it looks like head motion, but it has nothing to do with the head motion of my subject. Now, naively, I would say, okay, true noise models, that should fit lots of variance. All of these null hypothesis noise models, that shouldn't be fitting very much variance at all. It doesn't have anything to do with the data. But because of the fact our model is not complete, even these null hypothesis noise models are fitting substantial amounts of our data. So you can see sort of so the top center with simulated nuisance regressors and the ones from another subject on the top row, that's without pre-whitening. And you can see you are fitting significant variance throughout the brain. And that's not a good sign. But when we include pre-whitening, and I've done this with AFNI, and so this is an ARMA 1.1 model. It's a very standard pre-whitening for fMRI data. And when I've included that in the GLM, what you see is that the null hypothesis noise models are now going down much closer to random chance. It's on the order of 5% of voxels. You're explaining significant variance. So this gives me confidence that now my GLM approach with nuisance regression, it is more valid. I'm not having the same problems with overfitting. And so what I can conclude is that the ARMA 1.1 is sufficiently whitening the data in sort of standard fMRI data. So I checked the residuals to my nuisance regression. They were white. But what you see in this preprint by Bowman and colleagues, they saw the same thing when the TR was something on the order of 2 seconds. This is the optimal autoregressive model order to fit the residuals to your resting state data. And it is on the order of 1 to 2 order autoregressive model. But when you go up to much higher sampling, so now your TR is like half a second, you need a much higher order autoregressive model. And we can get into details of this, but suffice to say, if you change your acquisition, you can't just tick a box anymore. You are going to have to check that pre-whitening is working, among other things. So I've kind of made the GLM a lot more valid by using pre-whitening and checking whether or not my regressors were orthogonal and so forth. How can we also run into some complications when we're building nuisance regressors and trying to optimize it for a given cohort? That's the last portion of this talk. So the first issue is filtering. There are a lot of reasons why you might want to filter your data. We generally think that noise and signal might be spectrally very different, so a bandpass filter could differentiate the two. But you have to make sure you're filtering correctly. So if you just filter the data, like so, but you don't also filter your nuisance regressors in your model, you're going to find that the nuisance regression process is going to reintroduce the frequencies you thought you got rid of back into your clean signal. So the first thing is, if you're going to filter, you have to make sure you do it correctly. So you have to filter both the data and your model. But the bigger issue that I want to bring up is this idea of degrees of freedom and what filtering does. So this is a schematic on the left of different fMRI time series in the frequency domain. The maximum frequency that you can resolve with your time series is related to your sampling frequency of the original data, your repetition time, so TR. So the maximum frequency is 1 over twice your TR. And the sampling of frequencies within that range has to do with the length of your total scan. The longer you scan, the more sampling you have in that range. And so in gray, I'm demonstrating what a bandpass filter might do. That gray bar might be what you keep and everything else you throw away. You are getting rid of a lot of data there. When you go back into the temporal domain with another Fourier transform, you might still think you have 300, 600, 1200 time points, but your effective degrees of freedom is substantially reduced. And you need to take this into account. So the way I looked at this again was by getting a sense for what filtering does. Just simulate some data, just white noise time series, and look for correlations between them. So here in blue, that center, nice, normal Gaussian distribution, that is if you don't filter anything and you just have randomly generated time series, you get this distribution of correlation values between them. And the dashed vertical lines are that threshold of p is less than 0.05. That's your critical R value. And yes, about 5% of the time, you're going to exceed this critical value and think you have significant correlation when you know these were just randomly generated time series. That's what we've come to expect. And as you filter the data, what you see is that this distribution broadens. And you're going to artificially inflate your correlation values by filtering. And this will lead to an increased false positive rate. So I can't tell you how to correct the inflation of correlation values. That's just intrinsic when you have this filtering. But what you can do is correct your statistics to interpret what is significant. So I refer you to this paper here by Davy and colleagues, where they show you for a given filter that you apply, this is what you do to correct your statistic to get a new, those vertical dashed lines, you need a new critical threshold to say that something is significant. But again, I can't correct the inflation of the correlation values if you filtered. That means I can't correct for the fact that that nuisance regressor is just going to pull out more variance by chance. So my ultimate approach is to say, okay, if you're going to filter, filter with care, or maybe just don't. So if you're going to filter, you either have to do it after the GLM, or you have to do it before the GLM, as I showed you, identically to the noise model and the data, and you have to correct your stats. Or I guess the way I would generally do it is to try to incorporate this into the GLM itself. So put it into your signal model. Consider them additional nuisance regressors. Put in polynomials, sines, and cosines. And then the degrees of freedom issue is sort of taken into account in that fit. But I would just flag up that there is evidence for higher frequency contributions to the neuronal signal in resting state data, so filtering may really not be what I would generally suggest we do. The next pitfall you might encounter is temporal shifting. There are a lot of reasons why you want to shift a nuisance regressor with respect to your data. We know that there's going to be variation in the optimal lag between one regressor and the bold time series. So here's an example. This is a map of the delay between a CO2 regressor and the bold time series. This is over many healthy subjects, and you see this, this consistent variation on the order of many seconds in the optimal delay between the CO2 nuisance regressor and the bold time series. So you don't want to just use one regressor in every voxel, you want to optimize it. But this leads you to some issues. Let's look at this conceptually. Here's our bold time series. And then here, say, is a nuisance regressor, which originally has a correlation value of, I don't know, like 0.2 or so. And then we look at optimal shifts of this nuisance regressor. And we see that the correlation values then vary. And we might say, okay, the maximum correlation there is that second one, correlation of 0.36. That's our optimal shift. Let's use that regressor. Now, you have to be a bit careful here. If you just checked maybe one additional shift, because this is a low-frequency signal, you might get a very strong correlation, a negative correlation. So maybe this is your optimal shift. Overall, if you're going to look at lots of different lags and assess what's the best one, you have to take into account. First of all, you're going to, by definition, increase the correlation between two things. If you test A, B, C, and D, and you always pick the maximum correlation out of those options, you will always get something the same value or greater than if you just tested A. So your lag optimization will increase correlation values. But also, allowing long lags, you're going to start to see very strong positive and negative correlations, particularly when you're looking at low-frequency data. So going back to random time series, again, the blue curve in the middle is a nice normal distribution because I haven't looked at any temporal shifting. And you see a Gaussian distribution. You see 5% of the data is roughly falling outside of this critical R-value threshold that we can determine based on statistics, degrees of freedom, et cetera. However, as you start allowing for different shifts, so I'm plotting here, say we took into account plus or minus 1 TR as well as the original time series. What about plus or minus 10 TRs? We really don't know what the optimal shift is. Let's test lots of things. Well, you see that this distribution becomes bimodal. You can have positive and negative values. And you see this artificial inflation of correlation values because you're taking the best over multiple tests. So one thing, this again will lead to increases in false positive rates. You're going to see like a 60% false positive rate if you go to plus or minus 10 shifts. So you need to be aware of this. I'm not saying you don't want to shift, you do, but this is what it does. And one thing you could do is correct your stats. Again, this is a conservative approach, but the SIDAC correction lets you correct your alpha value for M tests. However, again, this corrects your interpretation of what is significant. It doesn't change the fact you've inflated the relationship in the correlation. So in real data, this is a resting state data and a breath hold data set from the same person. The black is the bold time series, and then below you see the original and then the optimal shift of the CO2 regressor. I wanted to see how robust we can actually identify the optimal shift, so I've plotted the one I determined in the first half of the data versus the second half of the data. It should be the same. It's the same person with the same physiology. With the breath hold data, you see a very good correlation between the two halves of the data, but we're dealing with resting state data, and you see there's complete scatter. We're not able to robustly identify the optimal temporal shift between CO2 and the data. So how can we get around this? This is my rather cutesy idea, I guess. I don't know. I'm sort of casually encouraging people to consider it. Resting fluctuations. The reason we can't find the shift very robustly is because there's not very much variance present in CO2. At the end of a scan, why not add a short breath hold? And then you get a bit more variance, and you'll have a more robust identification of the lag. This may or may not work. I haven't really tested it, but there might be something into amplifying noise so that you can characterize it properly to then understand what's happening in the resting state. I'm not really going to go into global signal regression. Like most of my colleagues, we're just avoiding this issue. It's still a controversial topic. It's free, it's easy, it contains all sorts of noise confounds that you might want to get rid of. But it does shift correlation values towards the negative region so that it's zero mean. And we know that there are neuronal contributions to this global signal. So removing it, it's a very loaded topic. I'll refer you to these papers. The one on the left is in the special issue about maybe reaching a consensus. Spoiler alert, they don't really actually tell you what you should do. And then the second paper is Cesar's paper, and I like his approach. He says, if you want to use global signal regression, justify it. And if you do use it, show what happens if you don't. And perhaps you want to consider some of these other techniques that don't use the whole brain signal, but just from more specific noise regions. And the final pitfall is model expansion. So I'm just plotting here the total model R squared for your noise model. Remember, R squared for the total model is kind of like the percentage of variance you're chucking out as noise in nuisance regression. Now, here is 3 random regressors in my noise model. They're just random white noise time series. And I'm seeing what that could possibly fit in the data. And when you have 3 time points, 3 nuisance regressors fits your data perfectly. You can explain 100% of the variance. But as you increase the number of time points in your data, that reduces dramatically. And that red line there is maybe a typical fMRI scan. Now, as you increase the number of regressors in your noise model, you're going to increase the amount of variance you're throwing away simply by chance. This is just how it works. And remember, these are white time series. This project gets a lot worse when your series aren't white, as is the case with nuisance regressors, which are generally physiological ones, are very low frequency, et cetera. So how can we look at this? I don't have a straightforward answer of exactly what you should do, but I do recommend you look at your noise model and generate some of these null noise model to compare with. So again, this phase randomization idea, this is a paper that explains it a bit better. But on the top are true noise regressors, and on the bottom are ones that have similar frequency components, but have nothing to do with your data. And then you can compare, is my nuisance regression really removing noise, something meaningful about the data, or is it just, out of flukes of statistics, removing variance by chance? So take-home messages. Nuisance regression, for all that I've just gotten you nervous about it, it is actually quite robust, and what we like about it is that it's hypothesis-driven. When you walk into a scan, you already know what noise sources you're going to try to model. You do need to check that the noise model you're using is appropriate for your cohort, and if you start changing your data acquisition, you may need to change your denoising. Like I showed you with very fast sampled fMRI data, you might need to change what pre-whitening model you use. You should keep track of ongoing developments in specific nuisance regressors and noise models and regression approaches, because this is an active field. And as came up in some of the questions earlier, the noise model itself might be quite useful if you want to understand physiological differences between participants or cohorts. And finally, just a plea, let's all make a point of writing really thorough, excellent methods sections so that we can understand what it is we're all doing and as a field keep improving. So I'd like to thank these gentlemen for their help. That's the paper in the special issue that talks about a lot of these simulations I showed you and corrections. And you feel free to contact me with questions, and I'll take some now. Thank you.
Okay, some quick questions.
So there were actually 4 reallys in that quote. Really, 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 really sucks. Because I got an email from Bill Newsom saying, does it only really, really, really suck, or does it really, 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 really suck? So it's 4. So I have to make a comment about global signal at this point. I see absolutely no reason in the world why you should have to justify global signal regression and not have to justify not using global signal regression. There is a lot of empirical evidence now that global signal gives you closer match between high and low movement groups. It takes the artifacts, the obvious frigging to the eye artifacts out. and it works. Does it move things to the left? Yes. But high movement subjects, their distributions are clearly moved to the right, creating a lack of negative correlations that exist in low movement subjects without regression. So the idea that, so I have a quote in my talk, which you may want to use again or not. Global signal regression is controversial. I see that in papers all the time, followed by, so I'm not going to do it. To me, this is very much like evolution is controversial, for example, in Kansas. Therefore, I'm only going to teach creation science. So right now, if there's any empirical reasons to choose one over the other, to me, it's obviously on the side of doing it. So to me, the justification should be, the burden of proof should be put on the other side.
Yeah, I mean,
know it wasn't a question.
I think this topic, it's loaded, and people feel very strong in either camp. I am not an expert in specifically global signal. I think what I always try to think about is, do I really know what the implications are on the data set I'm looking at? And so I'm not, I think that with different cohorts, global signal might feel very different, but I mean, this is something I would, again, you need empirical evidence to say if
So
it's...
all I can say is Jonathan now has the Gray Plot software where you can look at your data. Look at it and see if the denoising that you've done takes those large black bands out of your data. My guess is if you don't do global signal regression or one or two other kinds of things, like a ComCore 50 or something, you are going to have artifacts in your data. They will be differential between groups, and you'll get a group effect, and it'll be because of artifacts. So the literature right now is rife with artificially inflated group effects because of not paying attention to this.
I think if there's a take-home message to this whole session, it's that we need collectively to be very critical of all of our denoising approaches to make sure that what you're saying is not true in the future, that we do understand what denoising is appropriate, yeah.
How quick is it?
Oh, pretty quick.
Go.
Thank you for pointing out the pitfalls with not considering the statistical implications of varying the time lag that's used when you're trying to correct for physiological noise sources. Does this then require updating some of the previous literature that didn't correct for these variations in support of the value of physiological regressors?
So I haven't gone through all of the previous literature on this, but what I saw were a lot of people that did check out many different lags. So Karin Schmueli with heart rate, she looked at many different lags, and she tried to make her own kind of null hypothesis to convince herself it was more than random chance. And we also have some biological and physiological insight into what we think the relationship should be between a regressor and the associated, related, bold effect of that regressor. So I think with a lot of the physiological ones, I am not at all saying that we want to rewrite the past literature, but more that when you want to look at new cohorts that have very different physiology, you are going to have to do more optimization and to be a bit clever and careful.